Assalamualaikum warahmatullahi wabarakatuh. My name is Akilana Suhabiti Sarimin with metric number 1101466. I am a final year student of Applied Physics, Faculty Science and Technology USIM, and I am majoring in Computer Physics. My supervisor name is Dr. Ahmad Nazwa bin Rosli. Today I will explain about my final year project, which is the structural and intrinsic properties of pyrite, FES2, calculated using the density functional theory. First of all, the abstract of this project is the structural and the intrinsic properties of pyrite had been determined and calculated using the free source software of Burai 1.3 based on quantum expression. Then, the calculation will involve an exchange correlation potential of electron parameterized by Perdue-Emserhoff PBE under the generalized gradient approximation GGA functional scheme. Next, the optimization of structured pyrite with the latest constant of 5.4166 angstrom has resulted their bond length value about 0.622 angstrom to 4.7942 angstrom as measured between the iron and sulfur bonded atoms. The density of states, DOS for pyrite, are symmetric, showing that this material is non-magnetic, which have the peaks from negative 8.0 to negative 2.0 electron volt for the occupied valence band, and the peaks from 1.0 to 6.0 electron volt for the unoccupied of conduction bands. And then, the band gap for pyrite is around 0.4 electron volt, which we can say that this material is semiconductor material that more to the indirect semiconductor. Next, we move to the introduction. The uniqueness of pyrite structural and the good in its electronic properties that make pyrite be the human usage and be the useful materials along the development of technology nowadays. This mineral has a little economic value, but it is associated with valuable minerals of sphalerite, galena, and chalcopyrite. And then, the structure of pyrite has been studied with different techniques and properties, including their surface structure, stability, mechanism, and also their application in our life. A first principle investigation of the pyrite was reported based on Cohn-Shum DFT. The optimization structure of pyrite to the ground state energy and the alternate properties of pyrite were determined using the first principle pseudo-potential of DFT for the quantum espresso by discovering their band structure and the density of state. So, for the methodology of this project, we start with draw the crystalline structure of pyrite using Burai 1.3, a GI of quantum espresso, by taking the atomic position randomly. Then, the structure was optimized to the ground state energy mechanically using the minimization of forces mode by BFGS, which is Broyden-Fletcher-Goldfarb-Shannon algorithm. Then, the optimization of geometric structures and the plotting data for electronic properties of pyrite had been used, Burai 1.3, to study the density of state and their band structure. Next, all calculations were calculated using the first principle pseudo-potential method based on DFT and the plane wave method as implemented in quantum espresso package to solve Cohn-Shum equation using pseudo-potential wave function of core charge atom with exchange correlation term of GGA based on PBE functional. Then the calculation of SCF method is applied to solve the Cohn-Shum potential inside the simulation cell until the calculation is converged, and the convergence iteration for total energy calculated should be not 10, -6 Rybert. And now, from the table 1, it showed the details of input parameter throughout the computational calculation in this project. We start with cutoff energy of wave function. We use 25 Rybert. And then cutoff energy of charge density, we use 2 to 5 Rybert. And the minimized forces, we use 10, -3 Rybert of Bohr. The conversion energy is 10, -6 Rybert. And K-point sampling, we use 4 times 4 times 4 planar. The main objective of this project is to determine the structure of pyrite and to calculate the electronic properties of pyrite, which is their density of state and band structure. So, for the result that we got from this project, we start with the structure of pyrite that have been shown now. The structure of pyrite was optimized to the ground state of the energy using GGA-PBE as an exchange correlation approach. Pyrite crystallines have 4 FeS2 units in the primitive unit cell, while iron atoms occupy the vertices and center of the faces in the unit cell. Then, the lattice constant A of this pyrite was resulted as 5.416 angstrom, which shows that our reported results are quite similar and comparable with Dos Santos' research paper, because they were studying the same material of pyrite with another material which is arsenopyrite. Iron ion has coordination number 6 and the sulfur ion has a coordination of 4, which is 3 ferrum atoms and 1 sulfur. Iron atoms and sulfur atoms S2 can be said that they have a space group of Pa3. Next, we move to the result of density of state. From the graph, we can observe that the peaks from negative 8.0 to negative 2.0 electron volt corresponds to the occupied valence band, and the group from negative 2.0 to 1.0 electron volt to partially occupied valence band, and then the peaks from 1.0 to 6.0 electron volt to the unoccupied conduction band. Then, we can say that this pyrite has more occupied states than the unoccupied states because of the graph density of state plot shown. High density of state at specific energy levels illustrate that most states are available to be occupied. The symmetry of the spin up and spin down density of state for these systems describes the magnetic state of the material. So, the density of state for the simple cubic pyrite are symmetric, showing that the material are non-magnetic. Okay, now it's shown that the graph of band structure, based on the graph, it's shown that the band gap is said as the indirect band gap that between the lower part called the valence band maximum and the upper part is called conduction band minimum near the gamma symmetry. The band gap is at about 0.4 electron volt that we can suggest this pyrite is semiconductor material. Semiconductors are the materials with a relatively small band gap between field valence band and empty conduction band. The value of band gap in this project is relatively small compared to that of values reported in related studies, which is between 0.7 to 0.95 electron volt. This difference in the values could be attributed to the so-called underestimated value, in which DFT in LDA or GGA fails to correctly predict the energy gaps between occupied and unoccupied states. These results are comparable to other research that shows pyrite is indirect semiconductor with really small band gap appear. However, the value from this calculation is smaller compared to the other calculation as shown as table 2. So, for the conclusion, we can say that the structural properties of pyrite can be summarized as the simple cubic crystal structure, which had different length of bonds between the atoms that around 0.6224 angstrom to 4.7942 angstrom and have the lattice constant of 5.4166 angstrom. And then the pyrite crystallines have 4 FeS2 units in the primitive unit cell, while iron atoms occupy the vertices and center of the faces in the unit cell. The iron ion has coordination of number 6 and the sulfur ion has a coordination of 4, which is 3 Fe and 1 sulfur. The DOS for simple cubic pyrite are symmetric, showing that this material are non-magnetic, which have the peaks from negative 8.0 to negative 2.0 electron volt for the occupied valence band, and the peaks from 1.0 to 6.0 electron volt for the unoccupied of conduction band. And then, pyrite is semiconductor material that more to the indirect semiconductor because the band gap we got is around 0.4 electron volt, which is comparable with the previous research studies. Overall, we can say that the structural and electronic properties for density of states of pyrite is achieved, and the electronic properties of pyrite have been produced with band gap 0.4 electron volt. So, lastly, this is the list of reference that we use in this project. Lastly, I want to thank to the Faculty Science and Technology Museum, Dr. Ahmad Nazar Berosi, Dr. Azira Megaharli, dan all our evaluators. That's all from me. Thank you.